Oh, we're see. She's a constant. Yes. Why is there a T in? I know why there's a T.
Mr. Dawkins?
Hey, Britton, hold on, Britton. I'm helping somebody.
I'm sorry.
It looks like you just kind of threw a zero here and made everything solve for C. There's your condition. You gotta actually apply your condition. Yeah.
That shows it equal to 7.
Yeah. And technically, that shouldn't be 0. That should be whatever time. Phase 1. Technically, you can leave it as a 0 if you want to, but it's going to get you in trouble here because 20 hours after.
Yeah.
So if you set that to be 0, well, in this case, actually take it back. In this case, 0 will be okay. Okay. Because yeah, okay, either way, how you do something. But for you, because you use 0 here, yeah, then you won't choose 0. Yeah. Whereas if you use T sub C, you're going to T sub C plus 20.
Okay.
Yeah. So I kind of prefer the not doing 0 here. Do a 0 here. You basically saying you're starting, and you're not starting. You're continuing. Yeah. Okay. And I've seen people get themselves in trouble with zeros there because they basically when you do the 0 there, they basically forget that first phase existed, and then that gets in trouble. Yeah, right. So you got to be a little bit careful about that. And if I had just said, at time 20, that puts you in trouble because you want to put 20, but you could take it. Yeah, see what I'm saying? So basically, I don't care about this. It's not going to affect your answer here. Probably make it a little easier. Yeah. Just be careful with the 0. That's what's going on. Yeah, that's why this all knocked out on. It's basically you solve Z by setting it to 0. Plugged in. So you got 0.
Right.
Yeah. Just apply your condition. So get your difference equation all set up properly. Yeah. And then apply your initial condition and solve for C. Remember, C's got to be constant, so it can't be T.
Okay.
And that's what's getting you in trouble.
All right. So just do Q of 0 equals 700.
Yeah. Solve for C.
Solve for C, and then T will go away, and then plug in.
Yeah. Well, it's not that it'll go away. It's that it's that you're going to get a number out.
Okay.
And so. Okay, Britton, did you need something?
I was having some trouble hearing you at a point.
Well,
you were, but I didn't realize you were just helping. I thought you had already started and were trying to explain something before class began.
No. I never do lecture before class, ever.
Okay.
I ask questions. Okay.
Okay. I am very, very sorry.
That's okay. It was a student from my first class, and so it wouldn't have had any bearing anywhere for what you were doing. So.
Okay. Thank you for that explanation. But yeah, a warning. The weather's bad where I am, so I've switched over to some more stable hotspot on my phone, but I'm not sure if I'm going to be able to catch everything in this lecture. Well, I'm just giving you a head.
That's fine, Britton. That's what the recordings are for. Yep. Okay.
Okay.
So if your internet does, as long as my internet stays there, you can always go back and watch the recording later. Okay.
All right.
Okay. Where are we at? Yeah, go ahead and start recording. Okay, folks, I think it's time to get started here. Let's see, what do we got going on? So don't forget you've got homework today, yeah? Okay. So don't forget about your homework. Oh, okay, yeah, Jordan, okay. Yeah, so don't forget your homework tonight. Let's see, I was also looking at scheduling here, folks. At this point, I am still pretty darn positive. I'll know by the end of the day for sure. But pretty positive that your first exam will be a week from Tuesday. Okay, so be aware of that. I will send out an official announcement this weekend at some point in time. Once I get to sit down to think about where exactly I got through class today and how much time I'm going to need to get things done next week. But I don't see any problem with getting everything done next week for your exam on Tuesday. So at this point, just assume it'll be on next week from Tuesday, unless I say otherwise, but I doubt that I will. Okay, so we need to move on to another section here. Now, at some level, this section ain't bad. Of course, when I say at some level, that means what? That means there are definitely times where it can be bad. Yes? Okay. So, and sometimes I think the problem with this section, there's two bits where it comes into play here. One is that what we're doing can be a little bit tricky sometimes. You have to pay attention to it and watch what you're doing and not make a mistake with what you're doing. And the other problem can be, well, I'll bring that up when the time comes around. Okay, so at some level, it's not bad. At other levels, it can be really unpleasant at times if you're not paying attention to what you're doing. Okay, now the first thing here is our first problem here. So here's the first problem I want to work. I want to evaluate that integral right there. Okay, now the thing I want you to note here, folks, is what's up there in that upper limit. Oh, share screen. Sorry. Yeah, sorry, folks. Yeah, I apologize. Kind of been a bad morning here. Forgot to get it shared. I need to try to go better at that. I apologize for that. There it is. Sorry about that. Sorry about that. Okay, sorry about that. So back to here again. So here's the integral we want to take a look at. Yeah, so integral from 1 to infinity of 1 over x squared dx. And the point that I want to show here, folks, or point out here again, is this limit that's infinity now. This is something that you never saw back in Calculus 1, okay? And you didn't see back in Calculus 1, not because you couldn't do it, but simply because it was a topic that we didn't have time to do back in Calculus 1, okay? So first thing, then, this is kind of that, one of the first bit I was talking about can get you in trouble if you're not careful. Remember that infinity is not a number, right? It's a concept. You can't just blindly plug infinities in and expect things to work the way numbers work all the time. Sometimes you'll walk into the right answer. A lot of times you won't. Okay, so basically you can't just do this like a quote normal integral and then just plug infinity in and expect to get the right answer. Okay, so we need to be careful with this. All right. So what I want to do before I actually want to do this problem here, I want to think about something slightly different here. Let's just ask ourselves, if you remember back in Calc 1, kind of an interpretation of a definite integral was we could think of this as the area between this function and the x-axis. Yep. So think of that as the area. So make that clear here. Area between 1 over x squared and x-axis. Yep. So put a graph in here. Now, I only care about the positive part of this, not the negative, because we're just doing from 1 to infinity. Yeah, so I'll start at 1 here. And my graph for 1 over x squared is basically going to look vaguely like that. Yep, so I get closer and closer to my x-axis the farther out we go, but there it is. Okay, so basically we're saying, okay, I'd like to kind of know then what's the area, that area right there. Okay. That's equivalent question to asking what's this integral at some level. Yep, or at least equivalent in the sense that we know this is an interpretation of that particular integral there. Now, the first thing to note here at some level on this, folks, is we got to be a little bit careful about intuition with this, okay? Because again, I'm going out to plus infinity in this case, right? And since I'm going out to plus infinity, that means that this area here just keeps going out, going out, going out, going out forever. Yep. Okay. Again, obviously I can't do this on my screen here, but it goes forever. So intuition is going to tell us how much area should there be. If I go out forever, never stop it, what would that imply how much area I might have? I'll make a guess. Infinity. Yeah, good. And that is absolutely the guess that I'm guessing everybody was going to make with this. It's definitely the guess that I made on this the first time I saw this. Guess how much area there's not underneath here? Infinite. Okay? There is a surprisingly small amount of area under this curve. Despite the fact we're heading out to plus infinity, folks, there is not infinite area underneath that. Now, I know that doesn't make sense from an intuitive perspective, okay? But this is something you got to be careful of at this stage. One thing I always like to say about intuition at this point, and this will not be the first time I'll have to make this comment. What is intuition? Intuition is you've done enough things that we kind of have an idea of what's going to happen, and so our mind can just say, "Oh, this is what's going to happen." Right? That's what intuition is. The problem is how many integrals have we done that have infinite limits in them? Well, probably none. So what's your intuition? Well, none again, some level, because we haven't done enough of these things for intuition to be there for us, okay? So we have to be a little bit careful about this, even though we've got intuition for area, okay? And if I had a rectangle here, yeah, that had infinite length to it, hey, yeah, infinite area underneath that, no doubt about that. But I don't have a rectangle, and it's definitely not, a constant height of this thing here, yeah? So we need to be very, very careful about intuition. The thing I like to say at this point is basically I can and will break your intuition, right? Not only in this section, but in exam 3 set of material, I'm going to break your intuition all over the place there, right? So we have to be very, very careful about intuition at this stage and saying, because I think this is what's going to happen, therefore I know that's what's going to happen, okay? So I want y'all to be very, very careful with that, okay? All right, is that clear to everybody? Always got to watch out for that. Yeah, online, making sense? Well, maybe not making sense, but is it clear you need to be careful of your intuition? I should ask that instead. Yep, good. Okay. Now, because my intuition is not very good at this, okay? Well, actually, mine is, because I actually know what the answer to this is, obviously. But because our intuition is not very good at this, let's not ask this question first. Let's ask a different question first. Let's say instead, let me just stop it at some value, let's say t there. I don't care what I'm going to use. I just don't want to use an x because x is in my interval, right? So if I instead say, give me the area for that region right there. Now, that's pretty clearly not infinite. I don't have an infinite length here. My height is not infinite. So it makes some sense then. This can't possibly be infinite area. So it's one we can actually ask and answer. And we know how to do that. We know the area is integral from 1 to t, whatever that t happens to be. Yeah, let's keep that right for a second. I don't want to make a big deal about that down the road. So 1 to t. Okay? Now, 1 over x squared dx. Okay, so this then will give us that area there, right? And that's Calc 1. Yes, I don't have a number there for t, but I could put a number in. Yeah, 2, 10, 100, a million, whatever I want to. I can put a number in if I wanted to, okay? So this is Calc 1. So I'm going to let you guys kind of check my work on this. So let's start it back over here again. So by check my work, what I mean is I'm going to let you guys check my integral. Yep. Okay, so 1 over x squared, of course, is x to the minus 2, yeah, which integrates to minus x to the minus 1, but I just kind of went down to that form, so I thought it was a little bit easier for me. Okay, so let you guys check my integration work there. And of course, we evaluate from 1, be careful again, keep that t right. So evaluate from 1 to t, yep. Yep. All right, well, that evaluation is dead simple. We can all do that, I'm confident. So plug in upper, so minus 1 over t. Minus from evaluation, a minus there, so a plus, yeah. Plus. Make it clear, 1 over 1 obviously is 1, yep. Or let me just kind of flip the order around so I don't lose track of my minus sign there. So 1 over 1 minus t, yep. Now, that again? Oh yeah, that's that area right there. Yep. Yep. So maybe call that a sub t maybe. Yep. So the area between 1 and t. Okay? Just to give us something to call that. Okay. So there's my area there. Now, remember what I said a minute ago, though. T is just a number. It can be anything I want it to be. I could plug a 2 in. I could plug 100 in. I could plug a million in. I could plug a trillion in. Not sure what comes after trillion. Something bigger than trillion. Yep. Okay. We could just make it bigger and bigger and bigger and bigger. Right. So basically, yeah, the bigger that I let t be. So if I take t and I charge it out in that direction, it's always going to be a number. If I take it out in this direction here, bigger and bigger and bigger, shouldn't I be getting closer and closer and closer to the actual area? Because t is just getting bigger and bigger and bigger, quote unquote, closer to infinity. Yep. So, does that make sense? That idea makes sense, everybody? A little bit? Yeah, it's a little bit tricky sometimes, yeah. So our actual area, oops, not anymore. So the area I'm actually looking for, yep. Actual area, okay. We can kind of approximate it by just letting t get really, really large, yeah. And just keep letting it bigger and bigger and bigger, yep. Now, there's a name for that. Letting t get really, really big forever and ever. Keep constantly letting it get bigger and bigger and bigger. What's that called? If I do that process, what's that process called? Yeah, asymptote. Yes, that's kind of a correct algebra term. I should have been careful how I asked that, but yeah, I see what you're getting the asymptote out. That's not the word I'm looking for, but it is a correct answer. Yeah, but from a calculus perspective, if I let t get bigger and bigger and bigger, yeah, there you go, limit. That's what I'm looking for. Good, Santiago. Yeah. What I really want to do here is I want to let t get bigger and bigger forever. Well, that is equivalent to saying, oops, sorry, over there. Yep. That's equivalent to saying what I really want to do is let t charge off to infinity and take the limit as t charges off to infinity. Okay, that's what I'm saying I want to do. Okay, and in fact, when I do that, folks, this approximate here becomes equal. Okay, so what we have there then is our actual area. Oops. Down a little. So our actual area then is going to be equal to the limit as t goes to infinity of a sub t. Just letting t get bigger and bigger and bigger and go out forever. Okay? Or actually plug in limit t goes to infinity. I know what a sub t is, yeah? 1 minus 1 over t. Keep that t red again for a second. Okay, now I'd say we just talked about this, but that's my calculus 1 class, so we didn't just talk about this. But in your calculus 1 class, yeah, you know how to deal with things like this. So 1 over t to powers as t goes out to plus or minus infinity. Doesn't matter, plus or minus infinity, of course, gets bigger and bigger and bigger in the denominator. So 1 over 10, 1 over 100, 1 over a million, 1 over a trillion, etc., etc. Your fraction just going down to 0. Yep. So in the limit, 1 over t goes to 0, and limits of constants are always constants. So the answer is 1. Right? That also means, folks, there is exactly 1 cubic meter, 1 cubic foot, whatever your length units are, back up here, underneath that curve. Again, a surprisingly small amount of area underneath that curve. Again, I know intuition says that can't possibly be because we're going forever. Okay? But keep in mind again that our intuition is not going to work very well here because we're dealing with this infinite area stuff, or say infinite area, but infinite intervals. Yep. Okay. And because we're dealing with that, our intuition is not going to be very good about what actually has infinite area here. Jordan, yeah, let me, yeah, Jordan, I haven't actually worked this problem properly yet. I'm justifying how I work this problem. Okay, so yeah, so let me not answer your question quite yet. Yep, I don't got myself quite enough room here. So I'm gonna have to move this down for a second. So yeah, let me actually work the problem the way we're actually going to work this problem now. Okay, so here's what we're actually going to do. And Jordan, you've got a great question. It's not that I don't want to answer it. It's just that I'm going to kind of answer it through the rest of my problem here. So let me work the rest of the problem. So before we get there though, does the work that I did make sense from a physical perspective at some level? Yep. Because this is kind of the justification for what we're going to be doing here. Okay, so yeah, good, wonderful. So let us work the problem properly. Okay, here's how all of these problems will work from this point on, folks. Okay, so the first thing I'm going to leave yourself some space here. You have to write something in front of here. Okay, so leave my integral off the side over here. So first thing I'm going to notice is my real problem is this infinity up here. Okay, I don't like that infinity sitting up there. Okay, that's a problem for me because again, I can't just plug it in as a number. So the first thing I'm going to do is make the problem go away by just calling it a t. Okay, so make it go away. Although, are we really allowed to just make it go away? Does math allow you to do that? No, absolutely not. Yeah, if math allows us to make problems go away, none of us would be here because math would be easy. Yep. Okay, so we would just make the problem go away. So we're not allowed to just make the problem go away. So what I have to now do is say, oh, but I did have a problem at infinity, so I got to put it back in. How do I put it back in? I put it back in with that limit stuff I did up here. Okay, so I will now throw my limit as t goes to infinity in front of my integral. That's what the point of that space in front of there. Okay, so here's how, anytime you see an infinite interval, which is what these are going to be called now, infinite interval, i.e. there's an infinity in one or both of these places, know what I said there, touch that here in a little bit, infinity in one or both of these places here, we make the problem go away by calling it a t, in this case a t, and then we put the problem back in with this calculus 1 limit out in front. Okay, now quick little comment on the t's here, folks. Okay? The only letter you want to be careful of with this, folks, is don't use an x, because there's already an x in the integral over here. So basically, pick a letter that ain't x. Okay, I don't care what letter you want to use, but t is the standard letter that I use. Okay. Now, at this point, the problem works identical. So I'll kind of stay in black here for the rest of this. I want to kind of point out where the problem was here, so I was kind of doing the red here stuff. So at this point, right, do our integral. And we already did our integral up here, so I'm not going to rehash all of our integral. Yep, so do your integral. So 1 minus 1 over t. We'll do some problems, of course, all the way out. But do the integral, and then do the limit. And there we go. Okay, so again, like I said, I skipped the majority of the work, actually doing the integral and the evaluation and whatnot. But that is technically how we do these things. And Jordan, I hope that kind of answers your question as well. This is what on an exam or something like this is how you're going to need to do these. So strip straight to a t or flip straight to a t, put your Calc 1 limit in front, then do the rest of the problem, and then just evaluate your Calc 1 limit. So, okay, does that make sense, everybody? I hope. Yeah. Good. Okay. Now, let us, a little more room here maybe. Oops, sorry. So let me move this back up for a second. Move other things down the road. There we go. Okay. Now, I want to do exactly the same thing. Only now instead of 1 over x squared, I want 1 over x. Okay, so let me squeeze in the graph here. I'll make it super big. Sure I got enough room to work the rest of the problem here. There's the graph of 1 over x. Yeah. Oops. Hold on. Slow's not working. Okay, hold on here, folks. There we go. Okay, so here's my graph. Now, of course, my graph there doesn't look a whole heck of a lot different than my graph I had up here. Yeah. Okay. Except for what? Except it is different, right? It is different because it's an x versus an x squared. Okay? So, despite the fact they look the same, yeah, they are a little bit different. In other words, because it's x here, the line here is going to be a little bit higher up than the x squared. Yeah, so I didn't put an x squared in here; it would always be below the 1 over x line, basically. Okay. Now, again, I don't want to worry about intuition about how much area is underneath there, et cetera, et cetera. Right? So let's go through here. and just work the problem. We'll figure out the area stuff here at the end of the problem. But the problem now works exactly the way we worked the previous one. So I got a problem at infinity, so I make it go away. So 1 to t, or again, whatever letter you want to use, doesn't matter. Over x dx, and then put the problem back in with a limit out in front. Yep. Okay. Again, the thing that we're integrating doesn't change how these things work. Make the problem go away, put the problem back in. Okay. Now, the rest of this is Calc 1, literally. Okay, so the integral of 1 over x, of course, we've been doing these for a while now. That's just, natural log of absolute value of x, yeah. There it is, from 1 to t. Okay, do our integral limit evaluation. So plug in t, so natural log of t. Because we're going out to plus infinity, folks, it's safe to assume t is positive, so I'm going to drop the absolute value bars. You don't need to, but safe to assume. And the math log 1. There we go. Almost out of space here. I can squeeze it in here, I think. Now, I don't know if I've said this in this class or not, folks. I think I did the other day. Maybe. If I didn't, I need to say it here. For the most part, folks, I don't ever expect you guys to evaluate logarithms with the exception of logarithm of 1. Does anybody remember what the logarithm of 1 is? That's what I expect everybody to know. 0, thank you. Yeah, good, Michael. Yeah, and some are good. Yeah. So the only logarithm I ever expect you guys to evaluate for me is logarithm of 1 because that is 0. Every other logarithm, feel free to keep it. Okay. So, oops. So let's just get rid of that real quick to make it clear it's gone. Logarithm. Okay, so limit t goes to infinity of natural log of t. Yep. Now let's see here. Squeeze it in up here. 1 over x. Yep. There's the graph of natural log of x. Right. Yep. So 2 limits you need to keep in mind, folks, for natural logs because they can both come up into here. Okay. The second one won't make a lot of sense right yet, but it can come up in some stuff we're going to be doing down the road. Okay. So as I charge out to plus infinity, my logarithm just goes off to plus infinity as well. Okay. So that's the answer down here. I'll write that down here in a second. But as we go into 0 from the right, always think positive first because we can't plug negatives into our logarithms. But as I move into 0 from the right, my graph just charges down this way down to negative infinity. Now, again, I realize that doesn't look like that's going to have any bearing on these types of problems here, and it doesn't. But that can come up some stuff we'll do here in a little bit. So just keep that in mind, yeah? So my limit here is infinity in this case. So infinity for that one, and then 1 for that one. Okay? Now, everybody follow the work that I did there. I think, again, simple once you, again, keep in mind what you're doing. Yep. Yep. Now, this is the next thing I want to kind of talk about briefly here again, bring intuition back into play here again. Seeing that there was only an area of 1 under 1x squared, it would make some sense then that there could possibly be that much area under 1 over x, given the fact that the graph of 1 over x and the graph of 1 over x squared are nearly identical. This one's just a little bit bigger, so it makes a little bit of sense. There's more area underneath there. But again, surprisingly enough now, there is infinite area under 1 over x. Okay? Again, the graphs are virtually identical. You get out this range of a graph out here, folks. There is almost going to be any difference in the graphs. The graph between 1 over x and 1 over x squared is all going to be kind of the early part of my graph here. Visual difference anyway. Yep. Okay. But it turns out that that difference is just enough that it went from area of 1 up to area of infinity, which again is why I want you to be careful about intuition. It's very easy to break intuition for this stuff. Okay? Now, having said that, I don't want you guys to worry about area. Okay? I think that's a nice way to introduce the idea to motivate how we work these things, but for the most part, we're done with area. We're going to talk about it again. Okay? So, questions on these 2 examples before I move on to some definitions and some facts and stuff. We need to get out of the way before we work a couple more problems. So, any questions? Here. Okay, So, quick definition out of the way. Well, two definitions, really. Here it is. Okay, so we're going to call the integral, whichever one we're doing, so 1 over x squared. We're going to call the integral convergent. There we go. Yeah, I just put that there. Obscure the rest of my definition here. We'll call the integral convergent if the limit, the Calc 1 limit, the limit t goes to infinity, exists and is finite. And again, for finite, remember what we mean is not plus or minus infinity. Okay? We'll call the integral divergent if the Calc 1 limit either does not exist or is infinite. Right? Now, what does that mean for us? So up here, my first integral, yeah, integral of 1 over x squared, convergent or divergent? Well, my limit existed, was 1, so it existed, got a value, meaning existed, so I got a value, and 1 is pretty clearly not plus infinity or minus infinity, so this integral up here, scroll back up here and say, is a convergent integral. Okay, and again, convergent because the integral had a finite value, plus 1. It existed and had a value. On the other hand, this integral up here, yeah, we'll go over here, I guess, 1 over x, the limit existed, at least in some senses, and was infinite. And so in this case, our integral here, we're going to call divergent. Now, these two words, convergent and divergent, folks, are a couple of words that you're going to need to get used to. Okay, we'll do them in this section, we'll do them in the next section, and then it'll be 3 or 4 weeks, whatever it's going to be, before we ever see them again. And then when they come back up, we are going to be seeing them in pretty much every section, every problem of every section. Okay? So super, super, super important definitions for down the road. They'll be a little bit different when we see them again, but they're going to have the same basic idea. Okay, so keep these definitions in mind, kind of pay attention to what's going on. I'll say a little bit more about them here in a second, about kind of a good way to think about it. But we need to get this big blue box out of the way first. Yeah, okay, good. So, all right. So, don't worry so much about this if part of things here, folks, in front of things. What I want you to kind of focus in on at this point, folks, is that thing right there. Black there. Sorry about that. I want you to focus in on this bit and this bit. We'll deal with 3 here in a second. Okay. So, technically, for these to work, we need to kind of this initial part of things here, but I'm not so concerned about that with what we're doing here. Okay. So, if we have an integral that looks like this, from a to plus infinity of some function f of x, don't care what that function is, right? How do we deal with it? Well, we deal with it just like we did up here, because the first 2 I did is exactly this problem here, right? So we deal with it by getting rid of the problem, calling it a t, and then putting the problem back in with the limit, Calc 1 limit in front. In other words, this is just formalizing up what I did up here. Okay? Now, the second one here, folks, I want you to pay attention to. Right? Now I'm going to go from minus infinity up to b. Right? So again, remember I said earlier we can have infinities in one or both of these. So now I've kind of flipped it down below and I put a minus infinity up. Right? So from minus infinity to b. Now, how these work is, well, identical to what we did up above. I have a problem with the minus infinity, so I make it go away. I just call it t. Okay? Just like I did up above. And then I put the problem back in with the Calc 1 limit in front, only now it's going to be t goes out to minus infinity, because that's what my original limit was. Okay? So dealing with a negative infinite limit is exactly the same thing as dealing with a positive infinite limit. Okay. Does that make sense, everybody? Okay, good. Now, here's the tricky part. Okay, in this case, you do have to worry a little bit about this stuff up here on my line up above, but I'll hit that in a second. Okay, what I want to deal with now, folks, is what happens if there's infinities in both limits. So from minus infinity up to plus infinity, and that can definitely happen. Now, remember, I'll squeeze it in here. Okay. Remember, back in Calc 1 days, you had this wonderful little fact. You probably didn't use it terribly often, but you had a fact that said integral from a to b of some function, doesn't matter what it is. You can always split that up at some other value, say c, as long as I then started up a new integral at c and finished it out, yeah, and added the 2 results up, yeah. So again, you probably didn't use this terribly often, maybe 1 or 2 examples where that came into play. But it's a really useful fact. And it turns out that my limits don't have to be numbers. They can also be infinities, right? So in other words, I can use this fact up here because the problem is that I cannot deal with the integral, sorry, excuse me, I cannot deal with the integral if both of those infinities are there. Technically, the only two integrals I can do with infinities are these two up here. Those are the only two I can do. A single plus infinity there or a single minus infinity there. Those are technically only ones we can do. So how do I fix that? Well, I fix it by splitting up my integral. Where do I split it? It doesn't matter. Okay? Split it anywhere that makes sense for your particular problem. And we'll see how that works when we get to a problem down the road. Right? So that's how that works. Now, I got to be careful about that. Okay? And I cannot stress this enough, folks. This is the one case where you have to worry about this stuff up here. Okay? This equal sign here, folks, only works provided I have both of those two integrals convergent. Right? If one of these other integrals are not convergent, then this equal sign here doesn't make sense. Okay, so now, kind of how, at some level, I want to be kind of careful about this. I mean, why do they require convergent? Come back up here for a sec. Yep. If the integrals are both convergent, what does that mean? Exist. I don't care about that. What I care about is there finite numbers. Okay. Again, finite numbers means not plus or minus infinity. Okay. So basically, what this is saying is as long as these two numbers here or two integrals here are finite, in other words, they're two numbers, then I can add them up. Okay. The problem comes into play is what happens if one of the others is not finite or not convergent. Yep, meaning not finite, either infinite or doesn't exist at all. At that point, how you deal with the infinities or the fact that something doesn't exist kind of goes out the door. You don't really know what's going on. So basically, you've got to be very, very careful with this stuff, folks. Okay, now, the one thing I will say here is that it's a little bit harder to come up with the convergent, divergent stuff here, but I can come up with some problems down the road when this comes up, where this left side over here is convergent, but the two bits over here are divergent. Right? So that's where you got to be very, very careful about that kind of thing. Okay, so basically, again, this integral over here only works if both of my pieces are convergent. And I'll make a bigger deal about that down the road, at least a bigger deal than I already am. We get to a problem where this works, but I need to be very careful about that because people will abuse this on occasion. Okay, does that make sense, everybody? Hopefully, a little bit. Good. Okay, now, quick little fact here, okay? This is a fact, feel free to use. Well, I say feel free to use. What I really mean is feel free to use the next section because that's what's going to be useful to you, okay? So, quick little fact here. A to infinity, as long as A is a positive number, talk about why that needs to be down there down the road, okay? So as long as A is a positive number to infinity, 1 over x to the p, again, technically requires p to be positive, technically, okay? Although this fact will still hold into play even if it's not, but technically positive. Now, it turns out that this integral here, folks, will be convergent provided your exponent, whatever it is strictly bigger than 1. And it'll be divergent if your exponent is less than or equal to 1. Okay? In other words, up here, I didn't really need to do this work up here to know this integral over here. The first one we did was convergent. Because this first integral up here, my exponent was a 2. 2 is pretty clearly bigger than 1, so the integral had to be convergent. Okay? Likewise, here, the second one we did, exponent is a 1. Well, 1 is less than or equal to 1, so it's equal to 1. Excuse me. And so without the work, I knew this integral here was divergent. Okay? So useful fact to know because we're going to see a fair number of things like 1 over x to powers down the road in the next section. Now, having said that though, okay, I want to make this really clear, folks. This fact is only usable if it's in this form right here. Well, I'll allow a different number than a 1 up in the numerator. Minus 4, 10, 7, I don't care. I'll allow that. But the denominator has to be strictly x to a p, nothing else, okay? So x plus 1 squared, nope, can't use the fact. 5x minus 4 all to the 1/3, nope, can't do that, right? So it has to be strictly x to the p. I'll make a bigger deal about that in the next section because that's where it's going to become important for us, okay? All right, does that make sense, everybody? Okay, so let us then do a couple of problems. All right, so here we go. Start off. Minus infinity to 0. For integration purposes, yeah, let's write that as 3 minus x to the minus 1/2 because I know I'm going to want to do that for my integral eventually, so save me a little bit of space and get there a little step over. Okay, so there it is. Just like last time, or the stuff we did up above, and we talked about, the problem now is down here at the minus infinity, so I will make it go away, put a t in there, and then I will put the problem back in with the Calc 1 limit in front, minus t to the minus infinity. 0 stays there, and of course that stays there. Yep. So let's come down here. All right, so there's the first set. Okay, now at this point, folks, again, we're I don't say ignore the limit in front. You want to keep putting it in there, of course, yeah. But we're not gonna mess with that limit in front here for a step or two. Okay. All right. Now I'm gonna let you guys check my integral skills here. I think check this in a minute, make sure I'm right. I think that's what that integral should be. Get where I'm at in my notes so I can actually make sure I'm doing the right integral. Yep, good. Okay. Now, again, folks, I'm going to rip these integrals pretty quickly. Yep. Okay. At this point, I'm assuming you guys can do basic integrals. Okay. Meaning, how did I do this integral? Where'd that minus sign come from? And after this, I'm not going to spend a lot of time talking about these integrals. Yeah. Where'd that minus sign come from? So I'll guarantee some folks will wonder that. Anybody know? Technically, how did? Not the exponent. No. Good thought, but no. Technically, how did I do this integral? How did I have to do this integral? The du, yeah, good, Santiago, yeah. Technically, I had to do a u substitution, yeah. U equals 3 minus x. So your du is going to pick up a minus sign. It's going to come in from your du. Yeah, good. Basically, watch your substitutions, folks. It's going to be tempting to do a lot of these in your head. I don't have a problem with that. But it's also very easy to lose track of signs and stuff, yeah. So be careful with that, yeah. Oh, I should point out as well, folks, that all of my examples in this section in class are going to be stuck with Calc 1 integrals because they're going to go quicker. Be aware, though, that at least some of your homework problems are going to have Calc 2 integrals in them. That's where this stuff becomes unpleasant, right? They can be a lot longer problems. That's also, by the way, you got to be really careful about just plugging infinities in, right? That can get you in some serious trouble back there, okay? So be careful with that, yeah? All right. Go ahead and finish this one out here. So evaluation, so evaluate at 0, so minus, well, technically 3 to the 1/2, but yeah, let me get lazy, square root of 3, yep. And then minus of minus again, so plus, and we can do square root of the 1/2, doesn't much matter. Let me go back to roots because I want to make a point about this. So at least down the road I want to make a point about it in a later example. So again, just going back to roots there, the 1/2, so again, so I can make a point down the road. Okay, y'all agree? Yep, okay, good. Now we got to do our limits. Okay, well, limit of a constant is a constant, of course, so there we go. Plus, well, as t goes to minus infinity, the stuff underneath here goes to what? So if t goes out to minus infinity, what does 3 minus t go to? You can help me out with that one. Plus infinity, good, yeah. Plus infinity, yeah. Keep in mind, you can watch your signs and whatnot. Also keep in mind, folks, that polynomials always go to what the highest power goes to, yep. So we'll see some messier polynomials in here on occasion. Just remember, if you're going out to an infinity, whatever your highest power term goes to, that's what the limit will go to. Yeah, so good. So this goes out to plus infinity. What is the square root of plus infinity? It's a slightly smaller infinity. Okay, but that's it. Okay, so square root of basically infinity to a power is infinity. Yep. Or altogether, infinity. Okay, everybody follow? I hope. Good. Virgin or divergent? The answer up here. Is this integral convergent or is it divergent? Divergent. Good. Yeah, because again, that's the definition of divergent. Yeah, the limit either does not exist or is infinite. Yeah. Good. So write it up here. So integral is divergent. Now, pay attention to these problems, folks. Okay, I kind of zipped past this. I knew what the answer was going to be, but since I'm up here, determine if integral is convergent or divergent. If convergent, find its value. Divergent, you walk away. Okay, your answer is there. You're done. You walk away. Okay, but if it's convergent, my next one may or may not be. I don't know. Don't remember. Then we have to find its value. And if my next one's not convergent, eventually we will come across one that is convergent. Find its value. Okay, I want you to be careful with that. Yeah. Okay, so questions on that before I start the next example? Good. Okay. All right, next example, folks. Two infinities. Right? So here's where you have to pay attention to. Okay, so just like we did up here, what do? Well, I'm going to split this up somewhere. Where do I split it up? Again, it's completely and totally up to you folks, but I'm going to have to evaluate eventually. That exponential is not going to go away. So I think splitting up at 0 is a good place to do because evaluating exponentials at 0 are simple. Okay, so I will split this thing up at 0. You don't have to. You want to split it up at 5,002 all over 13. Be my guess. Kind of silly number, but you can do it if you wanted to. Okay. So write a problem down here. So minus infinity to 0. X e to the minus x squared. Gx plus integral from 0 to infinity. Remember, wherever you leave off here, you got to pick your second one up there. Yeah. Okay. There we go. Now, do this eventually. It's a little bit easier. Hold on. Get that. Go. Okay. Now, at this point, folks, this is where these problems begin to become just unpleasant at times. Okay. Because now I have two integrals to do. Oh, I should point out as well, again, folks, remember that technically, I don't know I can do that. Remember from my fact up here? Yeah, made a big deal about that. This only works if these two individual integrals over here are convergent. So technically, could I do this here? The answer is no, because I can only technically do this if I know that's convergent and that's convergent. Okay, that is the only way I can technically do that. Right, so what I'm going to do here for a second, I'm going to put a little red question mark up here saying to myself, I don't know that what I just did was legal. Okay, if it turns out I'm all done with my problem, that's convergent and that's convergent, well, I come up and I can erase my question mark because it turns out to have been legal. Okay. However, if it turns out that one of these was divergent, I should probably come up here and just erase the whole thing and pretend I didn't do it, or I didn't do something illegal. Okay, so keep that in mind. Yeah, technically I shouldn't be doing this, but we're going to get a little bit lazy and do it this way anyway. Okay. Now, at this point, now we got to do our problem. Okay, so I got to get rid of my problem here. I got to get rid of my problem there. So, first one, t, put the problem back in. Limit t goes to minus infinity. Okay, so the rest of our example here. There we go. Plus. Now, again, problem. Need to make it go away. However, what I don't want to do is I probably don't want to call it t, folks, because I'm going to have two limits out here. Yeah, one's going to go to minus infinity. This one's going to go to plus infinity. Okay, that's where my new problem's going to be at. So, oops, I'll use t there. Sorry about that. And what I don't want to do is I don't want to put a t here because then I got to be careful at the end which t is going out to which one. Right, so it's best not to reuse the letter again. I'm going to go ahead and just use the letter S. It's kind of what I tend to use here. I don't care what letter you want to use. Again, just don't let it be an X. Okay? Again, technically you don't have to do that, but if you do keep T's in both places here, just watch your limits and make sure you're using the right limit for the right T. Easy to mess up on occasion if you're not being careful. Yeah. Okay? All right, there we go. So everybody see how this gets built up here. Okay. Yep. Good. Now, suggestion. You do not have to do this or follow this if you do not wish to. But I'm going to suggest that your next step is to just do the integral by itself. Okay? Don't mess with limits or the integral limits. Don't mess with Calc 1 limits. Just off the side, say to myself, okay, I need to do this integral here. No sense doing it twice. So let's figure out what the integral is ahead of time, and then come back and finish the rest of the problem. Okay? This, of course, also is where your Calc 2 is going to come into play, folks. And by Calc 2, I mean for you guys, you will probably see, you will almost definitely see integration by parts show up in these things, and you can see partial fractions show up in these things. You won't see trig substitution show up. I'll guarantee that. Technically, they can show up, but I'm not going to make it. Okay, but again, just do your in-depth integral first, folks. Get that out of the way. Do it once, and then come back and finish your problem. Okay, makes your life a little bit simpler. So let's put our two problem children in there. So there's that one. Do the integral. So minus 1/2. Oh, and again, folks, a u substitution again here. Yeah, u equals the minus x squared. Again, I told you I'm going to stop doing our integrals here at some level. So there it is. Okay, there it is. Yep. Now the second problem one. Okay, so limit s goes to plus infinity. Okay. Squeeze this in here. So minus 1/2 e to minus x squared from 0 up this. Yeah. Okay, let's look at black. I just want to make my point clear about my colors here. Okay. All right. Now, again, at this point, folks, these problems can be long. And there's no doubt about that, especially when you've got some calculus here in the blue part. Yeah. Okay. So you got to be kind of very, very careful about that. At this point, what I'm going to suggest now, and even some level, didn't need to do this here at this point, what I'm going to suggest is kind of just do one of them. Yeah. Because if this one, for instance, ends up being divergent, I don't care about this one over here. I don't need to worry about it. Okay. So let's just do this first one. If it ends up being convergent, I'll come back and deal with the second one. Okay. So Casey, where are you getting the minus of a minus infinity? Are you talking here? If you are, you got to pay attention to your exponents. Yep. Yeah, watch your exponents. Yeah, that's not minus and minus infinity. I'll hit that in a second. Okay. Easy to get yourself in trouble on that. So do your evaluation. So again, plug in at 0. So e to the 0 is 1, which is why I chose 0. So just a minus 1/2, minus of a minus again. So plus e. Oh, sorry, plus 1/2. Sorry. Let me shrink this down a little bit here, folks. Need that shrunk down for next step here. Oops, sorry. Plus 1/2 e to the minus t squared. Yep. All right. I'm going to do the second one regardless, folks. I'm going to put the plus there, but let's just kind of do it the way I would normally do this stuff. Now, okay, this is where you get yourself in trouble. Yep. Okay. So do your limit here. Okay. Now, if you do your limit at this point, again, watching the squares. Yeah, remember the squares don't get that sign unless I put parentheses on. Yep. So I think we talked about this maybe the other day a little bit. So minus 4 squared. Side in case I didn't. I'm gonna have to erase because I'm gonna run out of room otherwise. Definitely gonna run out of room. That's minus 16. Yep. Versus this one, which is a plus 16. Yep. So if you want that minus sign to be squared, you got to put parentheses on. Okay. Without parentheses, this is essentially minus 4 squared inside of parentheses. Yep. Okay. So watch out for that kind of thing. So same thing with my limit stuff down here. Yep. Okay. So so when you do the kind of take the limit at minus infinity, as that goes out to minus infinity, the t squared goes to plus infinity, and then the minus sign here is going to go to a minus infinity. Yep. I'll remind you the formulas you need here for this as well. So my first term is going to be minus 1/2, okay, and then plus 1/2. Now, I don't remember, or I shouldn't say don't remember. I don't know what you guys did in Calc 1, okay, but you should have seen this in Calc 1. You did some limits at infinity. But when your exponent goes to plus infinity, the whole exponential goes to plus infinity, right? When your exponent goes to minus infinity, the whole thing goes down to 0. Okay, so in our case, our exponent is going to minus infinity, so our exponential has to then go down to 0 in our limit. Okay, does that make sense, everybody? I'll write that for me down here in a second, once I got how much space I've got. Okay, so there's my first integral. Everybody clear with that? Yeah, I'm gonna hope so. Okay, now, because my first integral up here was convergent, because I got a finite value here. Yep. What that means now is I gotta come back up here and do my second one, because I know I have to do my second one. Now, there's no guarantee this is gonna be convergent, of course. Yeah, I could have one convergent, one divergent, but because the first one I did was convergent, I've got to now come back and check the second one. Okay? So s goes to plus infinity. Again, do our evaluation. So minus 1/2 e to the minus s squared minus plus 1/2. Yep. Okay. Now, same thing here. Limit of my 1/2 out here is 1/2. So I'll put that there. And then this thing here, as s goes to plus infinity, again, the s squared is going to plus infinity, but minus s squared is going to minus infinity. So my exponent is going to minus infinity, which means the whole thing's going down to 0 again. So technically a minus 1/2 times 0, or better yet, 1/2. Yep. Okay, so first integral, convergent. Second integral, convergent. There it is, which then means that minus 1/2 plus 1/2 is 0. Yep. Do some stuff here, folks, a little bit more. Sorry, this is the problem with doing this stuff for the first time here. My spacing isn't exactly perfect on this stuff. There it is. Okay. All right. So let me squeeze in the rest of the problem right here. Yep. So what do we have here then? So at this point, what I now have is the integral from minus infinity to plus infinity of x e to the minus x squared dx is equal to 0, because it's equal to 0, okay, and convergent. Now, notice that this then does what I asked it to do, yeah? Convergent or divergent. If convergent, find its value. The nice thing about these problems, folks, is in determining whether or not it's convergent, you get its value for free, right? So you get to this stage and you've got a value, finite value, you know it's convergent, right? And again, if it's infinity or doesn't exist, it was divergent. If either one of these up here had been divergent, the whole thing would be divergent. I've got an example cooked up for that down the road. Okay, so any questions about this? See, we're at the time. We're not getting too far in the next bit, but we'll get a little bit. So any questions? Okay, now back in Calc 1. Yeah, definitely saw some Calc 1. Back in Calc 1, when you did definite integrals, or integrals in general, of course, I'm guessing that at some point it was made very, very clear to you, or at least I hope it was made very, very clear to you, that division by 0 was evil integration. Yeah. Right? So you had an integral, you had division by 0, you were taught it was evil, can't be done, shouldn't be doing it, and we just have to walk away and say integral doesn't exist or something along those lines. Okay? Now, we lied. We do that to you guys occasionally, unfortunately for you guys. Okay? It turns out that on occasion, note I said on occasion, okay? On occasion, some division by zeros are okay, and you can actually deal with them. Most aren't. They really didn't lie to you completely. Most times division by 0 is bad, it's evil, it can't be done. But there's an occasional time where division by 0 is legitimate and can be done. Okay? More generally called discontinuous integrands. In other words, an integral for which the function is not continuous. Now, again, depending on who you guys had for Calc 1, for me at least, I've got this quick and dirty definition of continuity, and that is that the graph has no holes or breaks in it anywhere. One way to get a break in there is have division by 0. Right? So, for you guys, basically division by 0. Okay, we're not going to see anything else other than division by 0 in this section or anything else with this stuff. Be aware, though, that there are other ways for things to not be continuous. All right, so I keep that in mind. All right, but for you guys, just division by 0. Now again, don't worry about this initial stuff up here, folks. Okay, other than to notice, I'll circle the important bit. My function is not continuous at b. It's not continuous at the upper limit up here. Right? What that means again for you guys is if I tried to plug b into my f of x here, I would get division by 0. Okay? Again, technically that's evil, but sometimes, yeah, it's not so evil. Right? So we can deal with it. All right. So how do we deal with it? Well, we deal with it exactly like we did the last step. Okay. We make the problem go away by calling it a t. Okay. And we put the problem back in with the limit. Now, again, let's be careful here, folks. When I get to an example, I'll make it clear why this is important here. A bit bigger off the side over here. Yeah. This is t goes to b from the left. You guys remember that right and left-hand limit stuff, I hope, right? From back in Calc 1 days. For upper limit being division by 0, this must be a left-hand limit. I will talk about why that is when I get to an example, okay? But watch your one-sided limits on this stuff. Now, be really picky about that stuff. The web assigned, of course, isn't going to care about it because your answer doesn't particularly care about it in the end. But when you come to do stuff for exams, I'm going to care about it. I'm going to look for it, right? So watch out for that, yep? All right, now, the other problem here, folks, is what happens if it's not continuous at our lower limit, at A, okay? Well, again, should make some sense here, okay? I make the problem go away by calling it a t, and then again, just like up above, it needs to be now a right-hand limit, okay? Again, I can't stress that enough, okay? Problem at the upper limit, left-hand limit. Problem at the lower limit, it's got to be a right-hand limit. Again, we'll talk about why, get you some examples, okay? All right, now, technically, again, folks, these are the only two kinds of problems we can deal with. If there's a division by 0 in the upper limit or a division by 0 in the lower limit. Technically, the only two we can deal with. Realistically, though, there's other problems, yeah? So one possibility is it's not continuous at C, where C lives somewhere between A and B. Okay, so somewhere between A and B, I got a division by 0 there. Now, at this point, just like with the infinite limits, because I can't deal with, I have to have the problem at one of my endpoints up here, folks. So what I can do is exactly that same thing that we did up in the infinite limits and split it up, right? The difference is now I have to split it at the problem point because the problem point has to be in the upper and lower limit position, right? So if I have 1 to 5 and division by 0 is at 2, I have to split at 2. Okay, so please be careful with that. Oh, also note again, folks, both integrals have to be convergent, just like the infinite stuff. Okay, so both of my integrals to do this have to be convergent. If one or the other is divergent, I can't do this. The whole thing's divergent. Okay, and we'll see examples of that down the road. Okay, and then one other possibility here. There's others obviously we could do here, but one other possibility is what happens if it's not continuous at both endpoints. Okay, so not continuous at A and not continuous at B. Okay, in that sense, again, all we're going to do is split it up somewhere. Now, in this case, this somewhere again doesn't matter. Okay, because the problem point's at A, the problem point's at B. So split it up anywhere it's going to be convenient for you. Do each of the integrals then individually. And again, noticing again, folks, both have to be convergent again. Okay. All right, so I know that this kind of doesn't make a lot of sense here, folks, so it's a lot of words at you, okay? Let's go through and see here. No, we don't have time to do a problem, so we'll do a problem on this on Monday. Excuse me, I'll show you the first problem. Nope. There's the first problem we're going to take a look at, okay? So we'll do this one on Monday, but again, pretty clearly, I have division by 0 at 3. Yeah, you plug in 3, obviously you have division by 0 down there. Now, before I let you go, one quick comment, have to think about this. Do not get locked into the problem always being at 0, folks, okay? I get folks all the time just saying, ooh, I see a 0 in here. I know I can't divide by 0. The problem's at 0, okay? No, that's not the case, all right? If the problem is wherever the problem is at, okay? That means you got to check your limits here. Make sure that limit you plug in gives you division by 0 or not. I have no problem with 0. I plug that in, I got square root of 3. I got a problem square root of 3, okay? I have a problem with at 3. So my problem is going to be up here at 3. Yep. So we will do this problem next time. But there it is. Okay. So Again, don't worry so much about the chunk of blue words up here. Yep, okay. It'll make more sense when we start doing some examples, so at least I hope it will. So I will stop it here. Stick around for questions, but you are free to go at this point if you'd like to. Yep, you too, Casey. Yep, you guys too.